All right, welcome to class, everybody. How's everybody doing today? Hanging in there till the end of the semester, yes? Okay, we are going to be talking about dimension reduction today, which is another topic that I like a lot. Before we dive in, any questions on any logistics? I just answered one question, which was yes, the deadline for the milestone has been extended by a day. So you have until tomorrow with no penalty. Any other questions? Okay, well then let's get started. So today we're going to be talking about dimension reduction, a super important topic in data science. And we'll talk about dimension reduction in general, and then more specifically, principal component analysis, or PCA for short. PCA is basically the simplest and the most popular thing out there for dimension reduction. So if you're only going to learn one method, you learn PCA. Of course, it's better to learn more, but we're doing our whirlwind tour, and we'll talk a little bit about using PCA for visualization. Okay, so here are some recommended readings. Chapter 10.2 from Introduction to Statistical Learning. And then there's this kind of cool little interactive explanation of PCA, kind of like we did with decision trees. You might want to just check that out and play with it a little bit. We'll also look at it together during class. Get that out. And then finally, the Introduction to Applied Multivariate Analysis, Chapter 3. Okay, so to get started, just all of our basic imports. The main new thing that we're doing here is this PCA function, which we import from sklearn.decomposition. So that's the main new thing that we're going to be playing with today. Okay, so just to put this in the broader context of what we've been learning in the course, we've had this kind of partition, right, into methods for supervised learning and methods for unsupervised learning. We've looked at, so in the supervised learning context, right, we have features X, and we have a response variable Y that we want to predict. So that's our goal, is to predict the response, and that could be in the context of regression, where Y is a quantitative variable, you know, like temperature or height or something like that, or in the context of classification, where we're trying to predict the class or category of an object. And then we've talked a little bit more recently about unsupervised learning. So what distinguishes unsupervised learning from supervised learning? You're both smiling, so somebody should say something. Yeah.
Unsupervised doesn't have labels?
That's right. Unsupervised, you don't have any labels, right? So you're still trying to like find some structure and visualize the data, but you don't have any labels to help you. So you're doing this in an unsupervised way. You only have the features, the data itself. And so one thing that we talked about in the unsupervised context was clustering, right? Can we at least kind of find natural groups in the data without access to any labels? And another area of unsupervised learning is dimension reduction, which we will talk about today. So in the context of what we're doing today, you know, we have some data set X, we've got a bunch of features, and we want to basically, we'll talk more about this, but we want to create a low dimensional embedding of that data, but it's without access to any labels. It's just visualizing the data itself. Okay, so that's what we're doing. Unsupervised learning. And in dimension reduction, what we are doing is essentially reducing the number of features in our data set. And because we may have thousands and thousands or even millions of features, and it may just be too many to work with. So we want to reduce the number of features. And there's two main approaches that you can use to reduce the number of features: feature selection and feature extraction. So in feature selection, you might carefully craft the features that you want to keep. This might require that you be a bit of an expert in some domain and that you know, okay, yes, I'm a biologist and I know that these are the important things and that we don't care about these other things, or I'm an economist and I know, but generally, if you're doing feature selection, you're coming at it with some kind of domain knowledge that gives you an intuition as to what's important and what's not, and you decide which features you think are relevant. That's not what we're doing. On the other hand, feature extraction, in feature extraction, the data is transformed from a high dimensional space to a lower dimensional space, and PCA is the most common way of doing that. It's a linear method, although there are other nonlinear methods out there, but we'll mainly talk about PCA today. Okay, and we've got a question. Labels, yes, thank you. I'm just running a bit behind there, yes. Okay, so why do we want to reduce the dimension? A lot of times we have a lot of redundancies in our data. So we may have thousands and thousands of features, but some of them are highly correlated with each other, and we don't really need to keep all of them because of the correlations. So we would like to remove redundancies. We also want some way of visualizing our data. If we have thousands and thousands of features, we can't make a plot of that. We would like to be able to make a plot where we can try to visualize the data. Also, from a storage and computational perspective, if we have a really huge number of features, it can be cumbersome even to store that much data. And also, if we want to run algorithms on it, they'll take a very long time to run, right? Even fast algorithms like k-means scale linearly in the number of features or the dimension. And so if you have a really, really high number of features, that can be problematic. Okay, so in order to store things efficiently, in order to run algorithms quickly, it's desirable to do dimension reduction. And in some cases, it can be helpful for denoising and also to avoid overfitting. Okay, and then I would say, in addition to, these two are like super foundational. You want to get rid of redundancies and you want to visualize. Okay, so that's our goal. So let's talk a little bit about PCA. So as we've noted, so the problem is that many data sets have too many features to be able to explore or understand in a reasonable way. And we can't even really plot these high dimensional data sets. So the idea of principal component analysis, or PCA, is to find a small number of features, think going from like thousands or hundreds of thousands down to like 5 or 10, find a small number of features, which are linear combinations of the old features that explain most of the variance in the data. Okay, so the principal component directions are going to be the directions in feature space in which the data is most variable. So I think to kind of get in, I think that's a lot to swallow, to kind of get an idea of what we're saying here, we can take a look at this little visualization. Okay, so let's take a look at this visualization. Let's say we start off with a data set like we have over here, which is just 5 points. What do you kind of notice about these 5 points? They're in a line, right? They look like they have this linear structure here. But the line, it's not lining up with like the x-axis or the y-axis. It's more like along the diagonal, right? It's not one of the coordinate directions. So if we were just to take the x values of all of those points, we could plot them here And they're about equally spread out with the y values of all of those points. Both the x values and the y values are pretty spread out and have a high variance. But as you noticed, these points, they lie along a line. They lie along kind of that red direction. And so the data is really varying in that red direction, and it's not varying very much at all in the green direction. So if we wanted, we could define a new coordinate system. We can make up our own coordinate system, and we could say, well, the first coordinate is going to be the distance along the red line, and the second coordinate is going to be the distance along the green line. And if we did that, we could replot this data, same data in this way, but now we have this red axis, which measures the distance along the red line, and the green axis, which measures the distance along the green line. The advantage of doing this is now, if we look at the coordinates of these points in this representation, what do we see? This is the values along the first axis, which we're calling PC1, and these are the values along the second axis. So what happened there? We notice that these, right, these are pretty spread out along that first coordinate, but in the second coordinate, they're not very spread out, right? So we kind of like put all of the variance into that one direction, into that one coordinate. So here, you've got a lot of variance going on, both in the X and the Y coordinate, but we found new coordinates representing the same data where all of that variation is just going in one direction, which is the direction along the red line. Okay, so the idea being here, maybe we don't even need the green, the green dimension at all. We could just throw it away and keep the red one, and that's really describing our data pretty well. Okay, so, but of course, really with two-dimensional data, you don't really need to do dimension reduction with two-dimensional data because, yeah, 2 dimensions is not too many. But it's good to sort of understand what this method is doing. Let's take a look at a 3-dimensional example. So now let's say we have this point cloud in 3-dimensional space, and we can these arrows are showing you basically the directions of first these arrows are just showing you the X, Y, Z directions. Now, if I do now when I hit the show PCA button, notice it computes a new coordinate system, right? Those arrows, they shift, they go from the standard XYZ coordinate axis. Now they follow this direction of greatest variance in the data. Now you see how this data set's really elongated along that red line, and it's picking up that direction of greatest variance. Okay, so then if we see, well, in the original coordinate system, we had about an equal amount of spread in the X, Y, Z coordinates, but when we did this new representation in these PCA coordinates, we were able to put a lot of the variance just in that one direction, the top principal component, and reduce the variance in those other dimensions. Okay, so that's kind of the idea of what we are trying to do. We want to find features that are good features in the sense that they account for a lot of the variance in the data. So how do we describe that mathematically? Let's say that we have a data set with P features. So we have X, which is X1, X2 through XP. So we've got, P dimensions to the data. And we want to define a new feature, which we'll call the first principal component score, as a linear combination of the original features. Okay, so we take all of our original features and we make a linear combination out of them. We haven't said yet what these weights, what these fees are, but they're going to be something. We're going to call this Z1 in vector notation. We can write this as phi1 transpose X, or the inner product of the vector phi1 and X. Okay, this vector, this phi1 that has entries phi j1, these are called the loadings. So phi j1 would be the loading of the jth feature on the first principal component. And that whole vector, phi1, would be called the loadings vector for the first principal component. Okay, so we want to pick this phi in a smart way. How are we going to do that? Well, we want to find the loadings, we want to find the phi so that this new feature, Z1, has maximal sample variance. So let's say I put all of my data in a big data matrix. I'm going to call this X. So X is going to be n, I have n data points, and I have by P, I have P dimensions. So Xij is the jth feature of the ith individual. And now, let's assume that we've centered our data. So basically for each feature, we've computed the mean across all individuals and we've subtracted it so that each feature has mean 0. We're just going to center our data. Well, then if you do that, a short calculation will show that the sample variance, that the variance of this new feature, Z1, is actually equal to the following right here. We're taking the average over points of this thing right here. And so we want this, what did I say? We want to find a feature that has a large variance. Well, we can make this arbitrarily large just by picking phi really, really big, but that's not really what we want to do. It's more about how big phi is, like how big certain entries are in relation to the other entries. So what we do is say, let's just constrain this vector phi to have unit norm. So let's say if we add up all of the squared entries in this vector, we're going to constrain it to be 1. Okay, so we're going to add this as a constraint. We're going to assume phi has norm 1. Then if we do that, the first principal component can be defined in the following way as the following constrained optimization problem. So we want to find the maximum over all possible vectors phi. We want to maximize the variance of Z1, which again, it remembers the inner product of phi1 and X, subject to the constraint that that vector has norm 1. Okay, and so actually, using linear algebra, how many of you have had linear algebra? Anybody? A couple people? Okay, so you were blessed with the discussion of eigenvalues and eigenvectors and all that fun stuff, right? If you haven't done that, that's no problem. But if you have, there's some interesting connections here with linear algebra. Phi1 happens to be the eigenvector corresponding to the largest eigenvalue of what's called the covariance matrix X transpose X. So here X transpose would be P by N, X would be N by P. This covariance matrix is P by P, right? And its eigenvectors will be P-dimensional vectors, which you can interpret as telling you different linear combinations of your features, which you can take. Okay, so that's what this thing is. And then similarly, you can define more of these guys. So that would be the first principal component would be defined from the largest eigenvector of this matrix. Then we can define the second principal component or the second principal direction to be from the eigenvector corresponding to the second largest eigenvalue of that matrix. and just proceed iteratively. Okay, and then what you're really doing there, you can think of finding that second feature. You want to find the next feature with the largest variance, subject to the additional constraint that Z2 is uncorrelated with Z1. You don't want to find features that are correlated with each other. You want them to be uncorrelated with each other. But this turns out to just be equivalent to those vectors, those phi's being orthogonal to each other. That is going to be automatically satisfied by the eigenvectors of the covariance matrix due to properties from linear algebra. So, okay. And then you can take as many as you like. All right, so before we look at this in Python, any questions on PCA or what we're doing here? Okay. Okay. All right, so PCA in practice. So like I mentioned, we can use the PCA function from the sklearn.decomposition library. Let's start off looking at the iris data set, which we have looked at a few times now. And you may remember that we have 50 data points here. We have 4 features on a collection of 50 flowers, right? We have 50 flowers, which are different kinds of irises, 4 features recorded for each one: sepal length and width, petal length and width. And we have 3 different classes or species of iris. And so we would sort of like to see the species like clustered together. That would be nice. Okay, but let's take a look at this. So we can just load this iris data, extract the labels, and then just create some color maps here. So if we want to visualize this data, what are our tools so far? So far, our tools for visualizing data like this would be, well, we can just plot the first 2 dimensions and ignore the rest, right? But the more dimensions you have, the worse that's going to be at really telling you what's going on in your data. You could try to plot 3 dimensions, but still that's not very many if you have a high dimensional data set. And you can also do the pairwise plot. So you've seen that a few times in lectures too, where you take each pair of features and do a little scatter plot. So you get this big matrix of scatter plots. That is useful, especially if you only have 4 features. But again, you can't really do that for thousands and thousands of features. Okay, so all right, so this is what we've done in the past. Just plot the first 2 dimensions, ignore the other dimensions. We can do that. We don't see very good separation when we do that between 2 of these classes. Here we can do the plot in 3 dimensions, and we can see maybe the separation a little bit better than we could in 2 dimensions. But it's actually a little bit difficult to even see what's going on here because the points get plotted on top of each other, and these 3-dimensional visualizations can be a little tricky. All right, and then here was the third way that we talked about, where we can just do the pair plot from Seaborn, where we plot each pair of features. And as we have commented on before, some of the features, we see a lot of mix-up of these 2 classes. Some of the other features, we see a lot better separation. So we do have a bit of variety here. Okay, so let's see how we can visualize this data with PCA, with our new tool. So first, we're going to specify that we're doing a PCA model. And then we're going to call this PCA model.fit transform. This is actually going to compute the new coordinates of the data. Okay, so the columns of this new array XPCA, those will be the Z's. Those will be the new features that we computed when we did PCA. And so now we can plot, right? Let's plot the first column versus the second column. And this is going to give us the PCA embedding of the data. Okay, so what do you notice compared with just plotting the first 2 dimensions of the data? Yeah, better separability, right? At least better separability than we saw in the first 2 dimensions. So somehow this is aggregating information across all of the different features and showing it to you in one plot. Okay, so that's super handy. So this is hinting at the fact that we can use PCA to visualize clusters in the data. And then one clustering method that you discussed, actually when I was not here, but you discussed hierarchical clustering, right? And so let's take a look at applying hierarchical clustering with an average linkage function to the data set here and specifying that we want 3 clusters. And then we can get a prediction. So what are the labels we would get if we just from clustering the data with hierarchical clustering, and compare those labels with the ground truth labels that are available for this data set. So if we do that, we can see that clustering based on the first 2 principal components of the data is giving us a V-measure score of 0.805. Okay, so that's, it's okay. It's not it's not bad. It's not amazing. It's just kind of okay, but it's definitely a lot better than we would have gotten on the first 2 dimensions. And visually, you can see the clusters matching up pretty well. Okay, so yes, right. And then this is the plot with just the first 2 features, as we already commented. The separation is not nearly as good there. Okay, so one important question that comes up when you're doing PCA is how many principal components should you use, right? If we're plotting the data, generally we can only do 2, at most 3. Those are just the limitations of data visualization. But it might not be enough. Maybe that's all we can do for visualization, but 2 or 3 dimensions might not really be enough to capture the structure in our data. So if we're asking how many dimensions do we need to keep to really, reduce the dimension, but still capture the important variance in the data, one way we can try to assess that is by looking at something called a scree plot. So let's take a look at this scree plot. So when you do PCA, you can access, this is really useful. You can access this quantity called explained variance ratio. And that's what we're going to plot right here. The explained variance ratio. Okay, so this was a 4-dimensional data set. So here we've got 4 different principal components. And how should you interpret this picture? So first we start off with 0.92. That's associated with the first PC, 0.05, and then it goes down. So this is telling us that 92% of the variance in the data can be explained just from the first principal component. 5% of the variance in the data can be explained by the second principal component, 1.7% from the third, and less than 1% from that last one. Okay, so that's a pretty high percentage, right? 92% of the variance in the data is actually explained just by that first component. Okay. And if you, well, to connect back with linear algebra, what are these numbers? These numbers actually come from the eigenvalues of that covariance matrix. Remember, each PC, each principal component, is an eigenvector, and it comes with an eigenvalue. If you take that eigenvalue and you divide by the sum of all of the eigenvalues, you're going to get a distribution, right? You're going to get a distribution telling you what percent of each one explains, what percentage of the variance is explained by each one. So these are directly computable. These numbers are directly computable from the eigenvalues. Okay. So let's take a look at another data set, which is a little more interesting because it's a little bit higher dimensional. And let's try to visualize some clusters here in the MNIST handwritten digit data set. So you may remember, because you've seen this one a few times now, these are images of handwritten digits. And we also have the labels indicating, whether it's a 0, a 1, a 2, a 3, etc. So this data set is used a lot in benchmarking of various learning methods. If you check out that link, I call a link to it. If you check this out, you can kind of see a summary of methods and their performance on that data set. That summary is based off of a higher resolution data set than the one that we have been playing with, but it's still interesting for a comparison of classifications methods which were implemented in scikit-learn on the MNIST data set. You can check out that link. Okay, so anyway, frequently used for benchmarking. So let's do a little recap here of what this data set looks like. Remember, we have 10 categories, which are the digits 0, 1, 2, 3, up through 9. We have about 180 data points in each class or category, and a total number of data points about 1,800. Now, each data point, each image has 64 features associated to it, lives in 64 dimensions, as it's an 8 by 8 pixel image, 64 numbers describing it. And so each feature, you have 64 features, each of those features can take on an integer value between 0 and 60. Okay, so some examples there. So let's load this MNIST data, and then we're actually gonna scale it. I think in your homework, you had the same data set and you played around with scaling and unscaling. And what did you find? Was the scaling helpful or not? I saw one nod, but I don't know. If I'm remembering, it wasn't like super helpful, but I don't know that maybe, I also don't know that it really hurt much. So I'd have to go back and look at that. I remember that it was a little bit unclear whether the scaling was actually helping you. Okay, so sometimes you have to think about, okay, so for this data set, it's maybe not 100% clear whether you want to scale it or not. We'll talk a little bit more on another data set where it's more clear. But anyway, let's scale it and we can try it without scaling for comparison if we like. Okay, so we're going to load the digits. We're going to scale the data. That's going to be, so X is going to be our features, Y is going to be our labels. And then this code, we're just printing some of these so we can take a look at what the data looks like. Okay, so let's use PCA to visualize this data and also to cluster this data set into 10 clusters. All right, so how do we do that? Well, again, we're going to call the PCA function. Here, we're going to specify that we only want to compute the first two components. Before we didn't specify, and it just computed all of them, right? We had 4-dimensional data and it computed 4 PCs. So if you don't specify, I believe it'll default to computing all of them, but you can say, nah, I just want the first 2 or however many. And then we're gonna fit that model to the data. Okay, so these are our new coordinates, our PCA coordinates. We've reduced the dimension of the data. So this XPCA will be about 1800 by 2. And now we are going to apply k-means to that PCA reduced data set to XPCA. We'll apply k-means with the k-means plus plus initialization and asking it to give us 10 clusters. And then we can assess how well it's doing with this V-measure score. Okay, so let's take a look. Actually, let me just maybe kind of scroll down here so we can visualize what this code is doing. This is the 2-dimensional PCA plot of the data. And then these little white X's are the centroids returned by the k-means algorithm when applied to that PCA embedding. And then we can actually, what the colors are, we can extend now to a model on points that have never been seen before, because if we have a new data point coming in, we could decide, okay, what's the centroid that I'm closest to? If I come in right here, I'm closest to this centroid, so I'm going to associate this point with the centroid. And so basically, once you have your 10 centroids, they define a partition of the whole space. Right, so we run k-means, we get these 10 centroids, and then we can think of that as defining these classification boundaries, if we like. Okay, so let's see, how well does this do? When we get a V-measure score of 0.46, is that good, bad? What would you say? What would we like that number to be? Okay, everybody's quiet today. My Zoom people should also chime in every now and then.
Don't you want it near 1?
Yes, yes.
So it's only explaining 46% of the variance within the data.
Okay, so careful. You're absolutely correct. We want it near 1, and this is a very bad value. We don't interpret this as explaining a percentage of the variance in the data. We could look at that from we would need to look at what the variance explained by the different components is, and we'll do that in a second. But this number is just telling you, how well the clustering is doing, basically a combination of accounting for over-clustering and under-clustering, and it's not doing too well. Okay, so we might think, well, okay, so when we did a 2-dimensional PCA and then we did clustering, it didn't go so well, and we got a very bad V-measure. Maybe we didn't use enough dimensions. Can we repeat this procedure with a larger number of dimensions? So let's say I try it, let's try it with a bunch of different dimensions. So let's try starting with 2 dimensions in increments of 2 up to 62. So if we do that, we can repeat this procedure. So for each choice of dimension, let's do the PCA dimension reduction with that number of components. And then let's apply k-means to the embedding. And then let's evaluate the clustering by comparing it with the ground truth labels. And so what do we see when we do that? We see that, yeah, things actually do improve if we use more dimensions, right? This is what we did with just 2 dimensions. If we use 3 dimensions, we go up to 0.6, and then we go back down. But basically, for the most part, we increase our V measure up to about 10 dimensions. It seems to be really helpful to increase. And then beyond 10, it's a little unclear. You kind of go down, up, etc. But definitely using at least 10 seems to be helpful. Okay. Okay, so great. Why don't we actually take our 5-minute break? And then we will wrap up. Oh, is there, and I've got a question in the chat. Is there an appropriate number of PCs? Like, is 30 PCs ridiculous? 30 PCs is not ridiculous, but it's really going to depend on, exactly. It's really going to depend on the data set. Yeah, so it's really hard to come up with a universal rule. But one thing that's helpful to think about is, well, I don't know, maybe in your mind, maybe you want to say, I would like for my PCA to explain at least 90% of the variance. If you have some kind of cutoff like that, then you can calculate how many dimensions you need to keep to get to 90% of the variance. Does PCA assume a linear relationship? Another question. Yes, it does. So PCA is essentially coming up with like the best linear combination of features, and what that boils down to is the best like linear fit of the data. But it will be problematic if your data is not linear. So if you have highly nonlinear data, the method can definitely not work very well. And is there a class exercise for today? I don't see one in the lecture folder. No, not an official one. I have like a question just at the end of the lecture file itself that if we have time, I'll have you try, but we don't have an official activity for today. Okay, so any other questions? Can the number of PCs exceed the number of features? No, they cannot, actually. So the number of PCs is at most the number of features that you have. Like if you have 3-dimensional data, you can have at most 3 PCs. The reason for that is if you have 3-dimensional data, those PCs are coming from the eigenvectors of a 3x3 covariance matrix. And if you have a 3x3 matrix, you have at most 3 eigenvectors. So you only have 3 eigenvectors going with a 3x3 matrix. So you can never have more than the number of dimensions. So that's good. It can never increase the dimension. Okay, great. Well, let's have a 5-minute break. I'm happy to continue to answer questions during the break, but feel free to take a little breather and we will come back at 4:30.
So if you didn't know what features to use for like a supervised learning method, then could you use this to help like pick them out or?
Yeah, so this can be helpful for like making features. If you just have really high dimensional data set, you have too many to use, but more in the context of like every feature is potentially equally useful, so you're kind of just trying to get rid of your redundancies by linear combinations, but it won't tell you which features are important for a specific task, right? Like, let's say you have genetic data and you do, you do PCA to map down the number of dimensions that you have. That can be really useful, but it's not going to necessarily tell you which genes are important for a certain disease or, yeah. But there's really no way to do that if you don't have like label information or domain knowledge to tell you which features are the useful ones.
I'm wondering, like, when we were doing all the scatter plots,
Mhm.
to see like and with model building to see like which features were most important to include. Are there, other methods of doing that?
Okay, so, but in that context, we had the labels, right? Yeah. Yeah. So are there other methods of like picking out?
Like if it was labeled, like what things do the same thing as that to help you make an intelligent choice for what features to include in a model?
Okay, so if you did have labeled data, then how do you decide which ones are relevant? Yeah, right. Right. So I guess, well, one way we tried to get at that was like linear regression, so which variables is useful to include in the model and how significant are they? So that's one approach. With we talked about KNN classifier. That's really not telling you which features are useful, it's just basing the classification based off of your distances, but based off your distances across all of the features. So in that sense, if you have features that are really inappropriate for your labels or just not informative for your labels, it might not work very well. But hopefully they're not, hopefully the labels have something to do with the features. Yeah, and then, so with support vector machines, you can basically, it'll give you like a decision boundary and you can actually look at what it is and it'll tell you, it's some explicit boundary defined by the features. So you could try to, dig into that and see like, okay, what's really the important features that are going into that decision boundary, but it would take a little bit of digging. And sometimes it's difficult because you have a bunch of features that go into it at once. Does that kind of?
Yeah, I guess I'm just, for the final project, I have like a really high dimensionality data set.
Yeah.
And I'm just trying to figure out like what the best predictive features are, like within it.
But you have labels, right?
Yeah.
But you want to know which features are the most relevant for those labels, right? Yeah. That is,
like you included a KNN or a.
Yeah, that kind of falls under the umbrella of something we're not really going to have time to talk about, but you could poke around a little bit if you're interested. Supervised dimension reduction. There's kind of an extension of this called supervised dimension reduction, where, the goal is the same, right? You're trying to reduce the number of features that you have, but you have labels available that are basically guiding that process and are helping you pick the space, pick the features that are actually relevant for why, but that could be something quite useful.
Supervised dimension reduction?
Supervised dimension reduction, yeah.
Yeah, I'll look that up.
Yeah. Okay, all right, I guess it's 4:31, so let's go ahead and come back and get started. Okay, so let's take a look at an additional data set. We'll do one more, well, probably two more, but this is the one we're going to do next. This example is from the 1988 Olympic I don't know how to pronounce it, heptathlon results. Okay, so what is this heptathlon? You know, this comes from the Latin root for 7 because it's an Olympic event consisting of 7 various sub-events, all kind of related to track and field. So you've got your 100-meter hurdles, your shot, your high jump, 200-meter run, etc., javelin. Okay, so so the values, you have all these 7 events. The values for each of these events are then combined according to the official Olympic rules to generate a score for each athlete in this event. And the athlete with the largest score wins. Okay, so we're going to take a look at some data. We'll use PCA to analyze it for the results for the women's heptathlon from the 1988 Olympics, which was held in Seoul, Korea. And so this is actually kind of a small data set. We have 25 athletes, and we've got 7 features that we're looking at, and these are in the CSV file in the lecture folder. Okay, so let's take a look. We're going to read in the data and then just take a look. So we have here the names of all the athletes and where they're from, and then we've got their scores in these 7 different events. And then the last column of this data is their official Olympic score, which was calculated according to the Olympic rules. Okay, so let's take a look. Describe, if we just do a little dot describe, we can get some summary statistics for each here, for the hurdles, the high jump, the shot, etc. What do you kind of notice about this data? Even if you just look at the means here, yeah, well, you notice that they're measured, they're just very different. And because these are like totally different events, they're measured on different scales and in different units. So the means here are kind of all over the place. The mean for the javelin throw, actually, that's not the largest. The largest one is for the run 800-meter event. And then I think the next largest one is for the javelin throw. And then some of them are smaller. Okay, so let's take a look at this data set with our pair plot from Seaborn. And so we can kind of get a look here. So what we notice is some of the events have a pretty strong correlation with each other, right? Like here we see a pretty strong correlation, but some of the events seem to be pretty uncorrelated. Right here, we've just got this like scatter. So we kind of see a big spread. Some of these events seem to have a negative correlation. Why do you think some of these events would have a negative correlation? Nope, got a chat. Some might be time, and some might be points. Yeah, right. Right. Some might be time, some might be points, or like distance, right? Like the javelin throw I think you're looking at how far you throw it. And so you want a high number there, so your top athletes are getting a really large number there. But for the races, you're trying to run them fast, your top athletes are getting really small numbers. So just depending on the event, we may see positive or negative correlations. Okay. Okay, and if we look at these plots, we notice there is one data point that tends to be really far away from all of the other guys. Notice this point right here. So in all these plots, we tend to have this data, this outlier. And as we have discussed when doing linear regression and correlation, those methods can be sensitive to outliers. So if you have an outlier, it can really impact your results. And PCA is the same way, because basically you're doing, it's kind of like linear regression. You're doing best fits. And so why don't we just take out the outlier? And this is maybe a good thing to try. Sometimes it's good to do the analysis with and without the outliers, but it's good to be aware of the fact that they may have a big impact upon results. So you might want to try it both ways, and then just make a note that you decided, if you do so decide, that it was best to take it out. Okay, so we're going to remove the outlier, and then we'll get rid of the name and the score columns, because we don't want to keep those as our features. We just want the 7 events. Here, right here, it's very important to scale the data, right? When we were looking at the MNIST data, we said, well, I don't know, maybe you should scale it, maybe you shouldn't, depending maybe on your perspective. But for this data, where we have different events measured in different units, measured on different scales, it's really mandatory that we scale the data. So what would happen if we didn't scale the data? Why do we need to scale the data? Any thoughts? I'm going to scroll back up here so we can take a look at what our different variables were and what their means and stuff were. Yeah.
It'd be like more variance in the ones which have a bigger range, which would disproportionately influence its component rank.
Absolutely. Yeah. So if they're measured on different scales, what are you going to see? You're going to see a lot of variance in this run 800 meters, just because it's measured on a larger scale, and also in the javelin throw, and then not very high variances in the other one. So if you just run PCA directly on this without scaling it, the linear combination that it comes up with, it's going to really weight the 800 meter event and the javelin throw. It's going to weight those a lot more highly than the other ones. It's just going to, pick out whatever the features were that were measured on a large scale, and you don't want that, right? So with this type of data, where you have features measured in different units and on different scales, you have to scale the data. And other applications, if it's all measured on the same scale, you might not need to do that. Yeah.
What actually is the scale doing? Is it just dividing by the range, or
Oh, great question. It's not dividing by the range. It is, it's scaling it so that each feature has a standard deviation of 1. Yeah, so first, when it scales it, first it centers it, first it subtracts the mean, and then it divides by the standard deviation so that the new normalized feature has a standard deviation of 1. But that does throw away some information, right? If you had a data set where everything was measured on the same scale, it's possible, that certain features, well, they just have a higher variance because they just have a higher variance, and they are the useful ones. So, you do risk that in this normalization procedure, you're going to throw away that information. So there's a potential loss there. But if they're, in many cases, there's nothing else to do. If it's different units and different scales, you need to do the normalization. Okay. Yes, very good. Prevents run variable from dominating. Okay, so that's why it's very important to scale here. So we're going to scale the data, then we're going to do PCA. And let's just take a look here. Right, so we do this PCA model.fit transform to get our PCA coordinates, and then make a new data frame here, a pandas data frame for future reference. And here we can take a look what PC1, PC2, etc. are. Okay. Okay, so now we have our new coordinates, our PCA coordinates, and we can actually plot these and label them with the names of the athletes if we want to. So here's a plot of the first two PCs, and then just putting the athlete label on top, so you can kind of visualize that. And then if we kind of go back to the question of how many PCs should we be using? Is 2 enough? Let's take a look. So we noticed before on the, well, we mentioned before on the iris data that if you're trying to answer that question of how many PCs should I use, a useful thing to do is to look at a scree plot, right? So to look at the percentage of the variance explained by each component and to see how that decays. So here, this is what we get for this Olympic data. We have the first component explaining about 62% of the variance, the second component about 13%, 12%, 6.7%, and then it decays. What we notice here, though, compared with the iris data, is that these percentages don't decay quite as quickly as they did in the other data. In the iris data, we had 92% of the variance just in that first component. And with this data set, if we wanted to capture 90% of the variance, let's see, we would have to keep maybe four of the dimensions, not one. Okay, so definitely we see a slower decay here in these variances, and that is going to lead to needing to keep more of the components. Okay, so looking at one of these plots, you know, how are you trying to read this off? There's a few different heuristics where you can look at a plot like this and try to decide how many dimensions you want to keep. One thing you can do is to, well, let's try to find where the largest gap in these eigenvalues occurs. And maybe that's what we want to do. So like we see the biggest drop in going from 1 to 2. So you could do that. That doesn't tend to be great all the time, because a lot of times you'll have really big jumps in the beginning where the eigenvalues are large. And so that kind of heuristic can lead you to maybe not keeping enough dimensions. Another thing you can look at is the ratio between these different values. Try to pick the point where the ratio of those things is maximized. You know, so there's different methods that you can do. The main thing is just to be aware of, you know, what is the percentage of variance explained by each component, so you can make a good call on how many you think you should keep. Okay. All right, so another thing we can look at here is, let's look, so we computed, you know, the PCA. If we look at the first principal component of this data set, we can compare it with the official Olympic score as computed by the Olympic rules. And what you notice if you do that is actually almost perfect correlation of the first principal component of the data with the official Olympic score. So that's kind of interesting. This is really sort of showing this first principal component is almost exactly the score that you get from the official Olympic rules. Okay, so that's kind of neat. And so you can kind of see the clear winner is Jackie Joyner-Kersee up here from the USA, who's kind of well separated from the other data points. Okay, so we've talked about this a little bit. How would the results have changed if we hadn't scaled the data? You know, they would have been dominated by those events which were measured on a large scale. So we could try that real quick. If we go back up here and if we rerun things without scaling the data, let's see what happens. Different looking plot. One thing you'll notice is that you see a faster decay in the eigenvalues, and that's because you're having more of the variance concentrated in those few features that were measured on a large scale. But this is not, you know, it's kind of an artificially artificial way that these are becoming small. It's a little bit misleading. Yeah, and then you can see you get a totally different plot here, and the correlation with the official Olympic score is now like 0.7, so it's now quite bad. So definitely we see the scaling was important. Okay, so great. So I wanted to ask for some thoughts on, now that we've talked about PCA and how to use it and how it's useful, what are some of the shortcomings of PCA? What are some of the limitations, maybe, of the method? Got something in the chat. Assumption of linearity. Yes, that's right. So this is a linear dimension reduction method. Basically, it's going to work really well if you're in a really high dimensional space, but your data happens to lie along a linear subspace of that high dimensional space. It will work very well. But if your data like curves all around, you know, if you've got surface that's like curving everywhere, or a sphere or something like that, it's not going to work. Any other thoughts? Yeah.
It seems like if you were only using like a couple of the components instead of like all of them, I mean, it would probably be better for generalizability, but like it wouldn't fit the test or the training set as well, because you wouldn't like have all the features there. I mean, like even if it was just like a couple percentage points lost, like it wouldn't fit your training as well.
Now that's true, right? Yeah, you're doing some compression, right? So you are in the interest of, you know, of reducing your number of features, you're throwing away some information, and that could potentially hurt your performance on something. Often it can help in terms of like not overfitting and generalizability and all that. But there could be circumstances where you throw away too much. Any other thoughts? There's kind of a big one we haven't touched on. And actually, this kind of relates to a question that you were asking about, like, which are the important features to keep? So remember, if we are, like, when we're doing this whole procedure, how are we making these features? Well, we're making them as a linear combination of all of our features. That's not exactly the most interpretable thing, right? If you're actually working in an application and you want to know each feature has a like physical meaning, you know, maybe you want to know, well, which genes specifically are important for, you know, my risk of cancer, or, you know, which, I don't know, which features in particular are important. Okay, maybe that was not like a great example because that seemed to be more in a supervised context, but the sort of lack of interpretability is a general limitation of PCA because we're making this linear combination out of all of the features. Yeah, it's hard to say exactly which features are the driving ones in terms of the variance. You can look at the size of the coefficients, you know, so if you see like, well, X1 and X5, they have a really big phi value, you know, they have a really big coefficient in that principal component that can indicate that they are kind of driving that feature, but it can be a little bit hard to interpret. There's generalizations of PCA, like sparse PCA, where you're not, where that linear combination, you can't combine all of your features together. Maybe you can only combine like 5 or something like that. Okay, so interpretability can be tricky, but it works very well for reducing the dimension if the data is linear. So in the last few minutes of class, let's dive into, well, not the interpretability issue, but the issue of what happens if the data is nonlinear. And we're not really going to have time to go into this, but I just wanted to kind of point out that, you know, this is an important thing. You know, your data may not be linear. And let's take a look at the MNIST data set. There's lots of different options for nonlinear dimension reduction. If you Google it, you'll find the Wikipedia page, which has got like way more methods than you ever wanted to see listed on there. But I'll just mention 2 more recent and popular ones that people are doing a lot now, and you'll see these in a lot of recent papers. The first is UMAP, and the second is TISNI. So if you want to try this out, a couple of installs you need to do for, first of all, for UMAP. The second one is just for plotting some things. Okay, but if you do that, then let's take a look at the MNIST data set. I'm once again going to load it and scale it, keep the same data that we were looking at before when we did PCA on the MNIST. And then here, I'm just going to compare. I'm going to do on that MNIST digit data set, I'm going to do PCA, just like we already did. And then I'm going to do a nonlinear dimension reduction method, TISNI, and another nonlinear dimension reduction method, UMAP. And like I said, we won't really have time to go into, well, what do these methods do? But I just want to show you, these plots so you can get a sense of how different the results can be. So first of all, we have the PCA plot. And now this is actually colored by the digit, by the label. We didn't see that in the previous plot. So what do you notice? In this 2-dimensional PCA plot, the digits are all over the place. We really don't see very good separation. And we noticed, yes, if you increase the dimension, it gets better. So by keeping 10 PCs, et cetera, we do get better separability. But in 2 dimensions, with the 2-dimensional PCA, the separability is very poor. Okay, now you can compare this with, this is what you get from TISNI. So this is what you get with one of the nonlinear dimension reduction methods. And this is not perfect by any means, but you can see how much better you can visualize those clusters just in 2 dimensions. With only 2 dimensions, we're still seeing really pretty good separation between the digits. The red ones, they kind of got broken up, like the ones kind of got broken up into some subclusters. Looked like it went did a little over clustering here, but it's still so much better to look at than the PCA plot. And then here is the UMAP plot, which once again, you can kind of see the cluster structure preserved really well there, okay? And so you may think that, oh, well, why do we ever do PCA at all if we have these nonlinear methods that seem to work so much better? There's pros and cons, right? So these nonlinear methods can be much better on nonlinear data that's curving around, describing it in a fewer number of dimensions. But sometimes they don't preserve some of the global structure that PCA does. Probably can't really tell from this plot, but maybe like we can see in the PCA plot, the red points are kind of in the middle. So the ones should kind of be in the middle of the other digits. Here they kind of are, but here they're really not, right? In the UMAP plot, they've taken data points that were kind of in the middle of the data in terms of the PCA plot, and they've pushed them off to the side. So they're sort of losing some of that global structure in the process. Okay, but still, these are still very helpful methods. And for data sets like MNIST, actually, you kind of expect that they aren't linear. If you have like an image and maybe you have like little rotations or little corruptions, one would expect that that would give you a nonlinear data structure. Okay, and one thing you can try out, we're sort of out of time for today, but you can try computing the V measure. So if you take these embeddings and then you run k-means in the two-dimensional t-SNE and two-dimensional UMAP embeddings, run k-means and then compare it with the ground truth labels like we did for PCA, and you can see what the improvement is in the V-score. Okay, so any questions on the nonlinear dimension reduction or anything else? Okay, well, you guys have a great evening. Good luck getting your milestones in, and I will see you Thursday. Yeah.
Like we're through it.
It's a lot, right? It's a lot of different things.
But very, very cool.